Hi students, in this video we're going to cover section 3.4 in your chapter 3 notes packet. Please make sure you are filling in your notes as you watch this video. So section 3.4 is the introduction to aqueous solutions. Now, in particular, we're going to focus on what makes something an electrolyte versus a non-electrolyte, and we'll get into something called solubility rules. So, reminders that an aqueous solution is when you have a substance dissolved in water, right? So that could be any substance in particular, but most of the ones that we're going to be seeing are going to be ionic solids dissolved in water. Now, some things, when you dissolve them in water, will create a solution filled with electrolytes. So what are electrolytes? Electrolytes are substances that conduct current or conduct electricity in solution. So you can have three different categories: strong electrolytes, weak electrolytes, or non-electrolytes. So strong electrolytes are when you have something that fully dissociates, so fully breaks up into ions. So 100% of the particles have divided into ions. A good example of a strong electrolyte is something like sodium chloride, NaCl, which when aqueous will break up into all sodium ions and all chloride ions. So those ions have electrons available to conduct electricity, hence why they are strong electrolytes. Now you can also have weak electrolytes. Weak electrolytes only partially dissociate, which means some of the particles will break up into ions, but some of them stay as molecules, which means they can conduct electricity a little bit, but not great. Weak electrolytes are things like weak acids and weak acids and weak bases. And we're going to learn a lot more about acids and bases later in the chapter. And then our third category would be our non-electrolytes. So non-electrolytes are exactly what they sound like. They don't conduct electricity. So how do you know if it will not conduct electricity? Typically, we're looking for things that are molecules only. So in other words, these would be molecular compounds, things made up of all nonmetals, because they don't dissociate into ions. In other words, they do not break up into ions. They stay as the molecules. Okay? Pure water would also be a non-electrolyte because we really have this neutral pH. It's not acidic or basic, nor does it break up into ions. So pure H2O, deionized water, would also be a non-electrolyte. Now, at this point, I am going to show you a demonstration. So I'm going to splice in a video demo here. Hi students, in this video I'm going to do a demo regarding electrolytes. So what I have here is a light bulb, but you see I have these two prongs on the bottom. They are not connected. Even though my light bulb is plugged in, it is not on. That's because our circuit essentially is incomplete here. So what I'm going to do is I'm going to put this into a number of different solutions so we can figure out which ones are electrolytes, meaning they are able to conduct electricity, and which ones are non-electrolytes, meaning they cannot conduct electricity. So I'm going to start first with our deionized water. Now, deionized water is pure H2O, so we would not expect that to have any ions available to conduct electricity. So let's test that out. As you see, very anticlimactic, nothing happens. Now, what about if I use tap water? So tap water does have some additives like fluorine and things for your teeth, so let's see if anything in there can conduct electricity. Now you see the light bulb does light up a little bit, but it's pretty faint. That's because there are some things available in here to conduct electricity, but really not too many, so it's more filled with weak electrolytes. Okay, now I'm going to use my deionized water for now just as a rinser, to make sure I'm not contaminating my solutions. Now next up I have acetic acid. And acetic acid is a weak acid, which we'll talk more about later, but weak acids are also weak electrolytes. What happens is the acid molecules, some of them separate into hydrogens and the anion, but others stay together and are molecular and do not conduct electricity and do not separate, so therefore they cannot conduct electricity. But if this is a weak electrolyte, we would expect our light bulb to light up, but a little bit brighter than our tap water, but still not full blaze, okay? So weak acids, like acetic acid, which is what is in vinegar, are weak electrolytes, same deal with weak bases. Okay, now let's test salt. Salt is an ionic compound, which means it will fully dissociate into a metal and non-metal, and we would expect this to be a strong electrolyte. Okay, so I took my salt and I dissolved that in water to give me a salt solution. You can still see some of it in the bottom of the beaker maybe. But when I dissolve that, remember, I'm expecting all of those ions to fully dissociate. I would expect a salt water solution to be filled with strong electrolytes. And notice, my light bulb is very, very bright, right? I don't want to look directly at it. I already made that mistake once. So much, much brighter than our weak electrolyte vinegar. Remember, as a comparison, here's the vinegar, a weak electrolyte. Here is salt, our strong electrolyte, because it's fully ionic and that whole solution is filled with ions. Now, remember, salt can only conduct electricity when dissolved, because that's when the dissociation happens. Now, my final beaker I have here for the moment is sugar. Sugar is molecular. It's made up of all nonmetals. So I would expect this not to dissociate into ions, meaning I would expect this to not be an electrolyte, or in other words, it will be a non-electrolyte. So we see nothing too terribly exciting happening here. Our sugar solution, sugar dissolved in water, is not producing any sort of electric current there. Now I have one final one just to round us out here. So what I'm going to do is I'm going to dump my DI water beaker and I'm going to exchange that for a sports drink. Now, any sports drink, especially Gatorade, but any sports drink always has on the label that they're filled with electrolytes so that you can get back to playing your sport as fast as possible, right? So let's see if that claim is really true. So I've got my sports drink here. If this really is filled with electrolytes, think about what we would expect to see with our light bulb. Here we go. Notice we see a very bright but a very bright light bulb here. That means that there must be a lot of electrolytes in this solution to conduct electricity, and that is exactly what we see. So there must be all sorts of different ionic compounds in sports drinks in order to allow electricity to flow and also to get you back playing your game faster. So I hope you found this little demonstration helpful. Okay, so you've just watched the demonstration video regarding electrolytes, and what we essentially saw was that our strong electrolytes have lots of ions in solution, so these would be our ionic compounds, as well as strong acids and bases. But we're going to talk more about acids and bases later in the chapter, as I mentioned. We also have weak electrolytes. Weak electrolytes will light up the light bulb not quite as bright as our strong electrolytes, a little bit weaker, but they can still conduct electricity a little bit because they have some ions there. So these would be our weak acids and bases. Again, we're going to talk more about those later in the next unit. Later in the chapter. And then last but not least, our non-electrolytes. These do not conduct electricity at all because there are no ions, so these would be your molecular compounds. You can dissolve them in water, but they're just not going to be able to conduct electricity at that point. So that is the difference between an electrolyte and non-electrolyte, and specifically strong and weak electrolytes versus non-electrolytes. Now, when you dissolve things into water to create a solution, you can get both ions and molecules. It depends fully on what's going on at the molecular level. Do you have these substances breaking into ions or not? And ultimately, we have a driving force behind these different reactions. So any reaction that happens in aqueous solution must have a driving force. So what are some examples of driving forces? One example is the formation of a precipitate, which is an insoluble solid that forms. Another example is if you have a gas forming, so that would, remember, show up as bubbles in an aqueous solution. Or if you're forming some kind of molecular compound, the common one you're going to see a lot is water. So the formation of water is another driving force for a reaction to occur. If you mix two things and they're just creating two more aqueous things with no gases, no solids, no molecular substances, there really is no driving force, so that reaction would not occur. But how do we actually know if things are going to dissolve or not? Well, it comes down to two things. If you are dealing with a molecular compound, which remember molecular compounds are all nonmetals, the molecule has to be polar. And for now, that might not mean too much to you. We're going to worry about that term in Chapter 8, so that'll be later in the year. For now, we're just focusing on this. If you have an ionic compound, how will you know if this substance would be soluble? In other words, it would dissolve in water or not? Well, it all comes down to what we call our solubility rules. And these are different rules that will essentially help you determine whether or not something will dissolve in water or will not. So we have a few charts here from the textbook, and then I'll also show you where these are in your reference book. So these charts from the textbook tell you some information. Things that are always soluble In other words, they dissolve in water, which means we would label them as AQ, would be substances involving sodium, potassium, or ammonium ions, or compounds involving any of these anions, nitrates, chlorates, perchlorates, acetates. All of those are always soluble. So if I have sodium nitrate, definitely soluble. If I have calcium nitrate, definitely soluble. If I have ammonium hydroxide, definitely soluble, etc. You also see that then most of our halogen anions are soluble, most fluorides, most sulfates, but then you start to see that there's some exceptions. So if I see, for example, the silver ion paired with chloride, instead of being soluble, AgCl would actually be an insoluble substance, which means it would be a solid, and we would name that, label that with the S for solid. Okay, so that's essentially what you're seeing down here. As long as you have one ion from the soluble compound list present, then that compound is going to be water soluble. Okay, so that's one way you can look at this. The other way you could look at it is just the insoluble things. So most of these ions, when paired with something else, will produce insoluble compounds, which means they don't dissolve. And we would expect that to be a precipitate, which means we would label it with the S for solid. Okay, so we see that there. Once again, you only need one ion from the insoluble list to make something insoluble overall. But the other way you can sort of keep these in mind and memorize these is they are in your reference book on page 16. So if you go to page 16 in your reference book, you'll see this page that I put in right here. Okay, these first six are telling you rules about things that are typically aqueous. In other words, they are soluble, meaning they do dissolve. Notice it lists the exceptions as well. So chlorides, bromides, and iodides are usually soluble unless they're paired with one of those three. Fluorides are typically soluble unless they're paired with one of these five, etc. But for now, I would say the big ones to focus on are these. Sodium, ammonium, and potassium are always soluble. So anything with any of those three are always going to be aqueous. And anything with your perchlorates, chlorates, acetates, and nitrates, same deal. So those don't have any exceptions, which is nice because those are helpful to remember. And then our ones on the bottom of the table, 7 and 8, those are showing you things that would be precipitates. In other words, they are solids in solution. Okay, so let's apply these rules. To finish off section 3.4, I gave you 7 different ionic substances here. What I'm going to ask you to do is use your solubility rules and label each of these as either AQ, which again, that means that it's soluble, it does dissolve in water, or S, which means it's insoluble because it's really going to be a solid. Okay, so take some time, use your solubility rules, and label each of these 7 as either AQ or S. Pause the video. When you're ready, press play. Okay, so let's see how you did here. When I look at these, first I'm going to start with my things that are always soluble. We said that ammoniums are always soluble, so that's going to be aqueous. We also said perchlorates were always soluble as well. We said nitrates, compounds involving nitrates are always soluble, so that's going to be aqueous as well. We also said acetates will always give you something that is soluble or aqueous. Now, the remaining ones, we have to look at a little bit more carefully. So if I look at this one and this one, which with our two group 17 ions, bromides and chlorides are almost always soluble with 3 exceptions: silver, mercury 1, and lead. Well, calcium was not one of those exceptions, so that's still going to be aqueous then. But silver is the exception. Silver paired with chloride, if it's normally insoluble, if it's normally soluble but it's an exception, that means this would be insoluble. That is a solid. That it would be a precipitate if that formed in a chemical reaction. Okay. Now, if you look at our remaining 2, if you find a rule for hydroxides or cesium, I don't see a set rule for that, but I do see a rule for hydroxides. It says that most metal hydroxides are insoluble, with the exception of our alkali metals, which is group 1, or barium, strontium, or calcium. Well, cesium is not one of those exceptions, so this is going to follow the rule that hydroxides are normally solids. And then with sulfates, our rule for sulfates is that sulfates are typically soluble. It does list some exceptions, but notice Mercury is not one of them, so that would still be aqueous. Okay, so that's how you're going to apply those solubility rules. Ultimately, we'll be writing these in actual chemical reactions as opposed to just freestanding compounds here, but that's how you would decide for an ionic compound whether you should label it as solid or aqueous in a chemical reaction. As always, if you have questions, please reach out.